All right, for example 4, what I'm going to do is instead of giving you the actual standardized value, I want to compute it, but otherwise it's the same as examples 1 through 3. And so what we're going to do is suppose that we have 32 samples. They have a mean of 20, a standard deviation of 4. So we're assuming that the population standard deviation is 4, and the mean is 22. So we're going to determine whether or not the null hypothesis should be rejected or not, where the null hypothesis is that the mean is in fact 22, or the alternative hypothesis is that the mean is less than 22. So this will just be a left-tailed hypothesis test. So given all this data, this is enough to actually go through and use our formulas. So let's jump back up just 2 slides to remind ourselves, 3 slides, I guess, to remind ourselves. We're just going to compute this formula for the standardized value, plug everything in, and see what happens. So what we're going to get z naught, that's going to be 20 minus, in this case, 22, because that's the value mu naught that we're comparing. So mu equals mu naught. So when we say mu naught, that's what we mean is that this value is mu naught, 22. Again, just to show you how that manifests itself in the formula for the two-sided, this is actually left-tailed, but mu equals mu naught, and then mu naught is that value there. Okay, so again, jumping back down, our sigma was 4, so this is divided by 4 over square root of n, 32. And it turns out that if we do this, what we're going to get is negative 2.8284. Okay, so that's what that standardized test statistic is. And so we're going to do either the critical value approach or the p-value approach. And if we do the critical value approach, what we're going to do is we're going to think about what is our critical value so that the area to the left of it, again, this is a left-tailed, and I know it's left-tailed because of the alternative hypothesis is that mu is less than 22. So that's the one that's consistent with being left-tailed. And what we're going to do is we're going to look at that, and we want to know, so we're going to look at that and we're going to figure out our critical value. So here we have to figure out what's the value so that the area to the left of it is 0.05. So it's going to be negative 0.05. So that's the value that we're going to have to figure out. And then you can figure this out either by looking at, there's lots of ways to do it. You can look at the table itself. So the table of the normal distribution, the z-values. On the t-distribution table, there was that little chart that had the z-values there. So you can look there. You can use R, so any technology. Whatever you compute, it turns out that the critical value is negative 1.645. Okay, so that's the cutoff, so that the area to the left of that will be 0.05. And that's one way that you could do this. And so you get the critical value. The test statistic that we get is negative 2.8, so that's to the extreme of that. So our negative 2.8 number is somewhere over here, negative 2.84. So this is our test statistic, right, z naught. If you remember the way that the graph looks, this is our rejection region, and this is the non-rejection region. Okay, so since our standardized value is in the rejection region, we're going to reject the null hypothesis. My pen has sporadically decided to stop writing, but we're going to reject the null hypothesis. Okay, so that's what we're going to do for this one, and that's how we make that decision. That's how we make that decision using the critical value approach. If we wanted to do the p-value approach, so if we wanted to do this using p-values, the process would be very similar. We would compute our standardized value, negative 2.8284. And then what we would do is we would compute the p-value. We would look at p-norm. In other words, what's the cumulative probability up to that value, negative 2.8284. And it turns out that that's going to be 0.0023. And since p is less than or equal to alpha, that means that we reject the null hypothesis. So we'll always reach the same conclusion depending on whether we use the critical value approach or the p-value approach. but yeah, it's really just two different ways of looking at the same thing. So in our case, we're going to reject the null hypothesis, whatever that stands for. 5 is going to be very similar. We're going to assume that we have, let's scroll there. So we're going to assume that we have, again, a sample mean of 12. So that's the mean of our sample. We have 40 values in the sample set. So there's 40 samples. The standard deviation, underlying standard deviation of the population is 2. And then we want to check whether the mean is 11 or not. Okay, so the way that we'll do this is very similar to before. You can do this using the critical value approach, where you compute Z naught and then compare that to whatever the critical values are. So we'll figure that out in a second. So here our Z naught would be 12. So X bar minus mu naught, which is 11, over sigma. Come on, pen. Over sigma divided by square root of n. This is really annoying, sorry. So divided by square root of n. Our sigma was 2. Okay, and so it turns out that if you compute this, what you're going to end up with is 3.162. Okay, so you end up with the standardized value of 3.1623. And you can again either do the critical value approach or the p-value approach. So the critical value approach, let me just organize this a little bit better. The standardized value is what you would get, and you'd have to compute that whether you use the critical value approach or not. The critical value approach says, well, this is going to be a two-tailed test because the mean is not equal to 11. That means that it could be less than or greater than. So it's two-tailed. And we want to know the 5% significance. So that means that we're going to look at z sub 0.025 and the corresponding negative value, z sub 0.025 with the negative in front. And it turns out that those cutoffs are going to be 1.96 and negative 1.96. Our test statistic that we computed is 3.1623. So that's somewhere over here. It's in the rejection region. So it turns out that we're going to reject the null hypothesis. Okay, so we will reject the null hypothesis. That's one way to do it. Again, another way to do this is with the p-value approach. So the idea here is you could compute the p-value, and the p-value is going to be, in our case, it's going to be 2 times p norm. Basically what it's going to be, let me actually tell you what we're computing first. Here's our test statistic, z naught. We're going to take this area to the right of z naught, or the area over here to the left of minus z naught, and we're going to add those up. So those two orange areas added together are going to give us, so this will be 2 times p norm of negative 3.1623. And that's going to turn out to be 0.0016. Okay, so this orange bit is the p-value that we're looking for. So let's just make that a consistent color there. So that's 0.0016. And again, our p-value is less than or equal to alpha, so we're going to reject the null hypothesis. Okay, so it turns out that either way we want to do this, whether it's the critical value approach or the p-value approach, we're going to reject the null hypothesis. Okay. In the final two examples, what we're going to do is we're going to look at this set, but here we don't know the underlying population standard deviation. So we're going to have to use the t-distribution. Other than that, everything's going to be basically the same. Okay, so we'll have to walk through and look at this. So for number 6, we're going to look at the, let's use blue. We're going to look at the studentized value t naught, and that's going to be x bar minus mu naught, so 20 minus 19, over 6 divided by square root of n. So divided by, so s over square root of n. And that's going to turn out to be 0.9428. Okay, and so we could do the critical value approach or the p-value approach. Again, whatever you want to do there is fine. It's 0.942. Let me try this one more time. 0.942, I think it's 0.9421, not 0.9428. I think it's 0.94208, 0.9421. What it's not going to make too much of a difference here. For a critical value, what we're doing is this is going to be a right-tailed test. So we're going to look at, this is the t-distribution, um, and we're going to run a 5% significance level test for a right-tailed test. So that means that we're going to look over here for t sub 0.05, where we have 31 degrees of freedom. Okay, so we have 31 degrees of freedom because we had 32 data points. And so if we want to compute this critical value, what we could do is, there's again a few different ways that we can think about this. We can compute the value using symmetry, or let's just do this. So what we want to do is let's look at, this will be Q for, because we're going to give it the probability and we want to get the actual value. So this will be QT of 0.95, and we have 31 degrees of freedom because it's 32 minus 1. So that will give us our cutoff, t sub 0.05. And it turns out that that cutoff is going to be 1.696. You could also do this, by the way, by looking at, let's see, how else could you do this? This would be minus QT 0.0531. Okay, so that would give you the same 0.1696 number for our critical value. And then from that, we can do a few things. So if we do the critical value approach, we're done. So this T naught value, this T 0.05 value rather, here, this is about 1.696. Our test statistic that we computed was 0.94. That's going to be in the fail to reject zone. So we fail to reject. Okay, so we fail to reject the null hypothesis. Okay, so that's how that'll work there. Or we could do the p-value approach, and the p-value approach would be similar. So for the p-value, we look at 0.9421. This is going to be this is going to be a right-tailed test. So that means that the p-value that we would look at would be, there's again a few different ways to look at it, but the p-value is going to be 1 minus, really what we're trying to do, let me just emphasize here, we're trying to find this area. So that's going to be 1 minus the cumulative probability up to 0.94. So that's going to be 1 minus the cumulative probability up to 0.9421, again with 31 degrees of freedom. And it turns out that our p-value would be about 0.1765. So again, since the p-value is greater than our alpha, we fail to reject. So I don't want to say too much more, but our p-value is greater than alpha, so that means that we fail to reject the null hypothesis. And then finally, on our last example, so example number 7, we're going to have a mean of 12. We're going to have 40 data points, so sample size of 40. Our sample standard deviation is 4. And then we want to know, it's a two-sided hypothesis test. So we want to know, is the mean 14 or not? And we're going to use a 5% significance level. So what we're going to do is, let's just draw a picture. I really like drawing pictures for these. It really helps make these a little bit more intuitive. We have a 5% significance. It's two-tailed though, so we're going to split that 5% into 2.5% up here and 2.5% down there. Okay, so we're going to consider what those cutoffs are. And again, we could do this one of two ways. So I think what you could do is you could do, oops, let's do QT of negative 0.025. And that would give you the negative value, and then you can take the positive value to get the value on the right side. But this would give you negative 2.023. And I forgot, this wouldn't give you anything. This would give you an error because I forgot to include that we have 39 degrees of freedom because we have 40 data points. So if we plug those in, we would get negative 2.023, and then by symmetry, the value on the right would be 2.023. And we would also have to compute our test statistic T naught. T naught would be x bar minus, so in this case, 12 minus 14 over 4 divided by square root of n, 4 divided by square root of 40. And when we do this, we're going to end up with negative 3.1623. That will turn out to be our studentized value. So that's what it is, negative 3.1623. If we think about these values here as being, let me just raise this up a little bit so we can draw on it a little bit nicer. So this is the value over here, 2.023, and likewise negative 2.023 over here. The value that we found was negative 3.1623. That puts it squarely in the rejection region. So we're going to reject the null hypothesis because it's less than our critical value, right? It's in the rejection region. Okay, so in this case, we'll reject the null hypothesis. Alternative, and that was the critical value approach. Alternatively, we could do the p-value approach. In the p-value approach, what we'll do is we'll compute the p-value, and that will be, so p is going to be 2 times the probability of getting something as rare as negative 3.1623. We're going to have 39 degrees of freedom. It works out that this is going to be 0.0030. So since p is less than or equal to alpha, alpha is 0.05, p is 0.003, p is less than or equal to alpha, so we reject the null hypothesis. Okay, so in a nutshell, these are some good examples. We haven't worked with actual data yet. That'll come soon. But given sample means, sample sizes, sample standard deviations, and so on, this is enough to be able to run a hypothesis test.